Hi, so today we're going to be talking about the continuity of functions. Continuity probably reminds you of the word continuous, and all continuity for functions means is that there are no breaks or any interruptions in the function, which basically translates to if you were drawing a graph of the function, you could draw the whole graph of the function without your pencil ever leaving the surface of the page. So you would never have to pick up your pencil, put it somewhere else, and then continue drawing. So there are three conditions that have to be met in order for a function to be continuous. And they're on your screen now. So the first is that a function is continuous if f of c is defined, which means if you plug a c value in, you're going to get a number out. You're not going to get something that's undefined. The second condition you want to look at is see if you can take the limit as x approaches c. If you can, if this limit exists, then you're good to go. Look at the third condition. So the third condition kind of smushes the first two together, and it says that not only does the limit at x approaching c have to exist, it has to equal to the function value at c. So those are the three different things you want to look at to determine if a function is continuous at a point c. A function can also be continuous over an interval, which just means that all three of these conditions have to be met for all of the values inside of the interval. Okay. So then we have two different types of discontinuities that a function can have. The first type is on the left, and it's called removable. And what these look like on graphs is they look like holes in a graph. So visually, that's how you could see them. And these happen when the function value doesn't exist. So these happen when f of c does not exist, but the limit still exists. So the limit as x approaches c of f of x does exist. So that's when a removable discontinuity is going to happen. But you can see this if you're working with a function. This is going to happen when you have common factors between the numerator and the denominator. So if you have a common factor and you can cross them out, you're going to have a removable discontinuity at the x value that would make that factor equal to 0. So we're just going to abbreviate the numerator and the denominator as num and din. Okay, so then the other type is non-removable, and what these look like are vertical asymptotes on a graph. And those are how you would see them visually. But these happen when both the function value, so when both f of c and the limit do not exist. So when both of those things happen, you have a non-removable discontinuity. And you can see these when you're working with a function. These happen when the denominator is equal to 0. And there's nothing to cancel with it in the top. So again, we use our abbreviation denominator equals 0. So the type on the left, the removable, is called a removable discontinuity because you could redefine your function and plug in the hole in the graph and make it go away. You could remove the hole there. And then non-removable discontinuities are called non-removable because there's no way that you could bend the ends of the function together in order to make a smooth and continuous function. You can't bend a function without completely changing it, so it's non-removable. Okay. So now we're going to go over an example where you can see both a removable and a non-removable discontinuity. And we're going to do that by looking at the function f of x equaling x minus 5 over x squared minus 25. So we can factor the bottom. So when we do that, we get x minus 5 over x minus 5 times x plus 5, because it's the difference of perfect squares. So now we see we have a common factor on the top and the bottom, the x minus 5, so we're going to cross those out. So when we cross something out from the top and bottom, it gives us that hole in the graph. So we have x minus 5 equaling 0, or x equaling 5. So that's going to give us a removable discontinuity at x equaling 5. Okay, so now we're going to just rewrite what we had. So now we have 1 over x plus 5. So we have something in the bottom, and if we set x plus 5 equal to 0, we get x equaling negative 5. Because there's nothing to cancel with that x plus 5 in the top, we're going to have a non-removable discontinuity here. So that's how you go about finding them. If you were asked to remove the removable discontinuity, you'd want to plug in the hole. So you'd want to redefine the function by using a piecewise function. So you'd want to write f of x is equal to 1 over x plus 5 when x does not equal 5, and 1 over 10 when x is equal to 5. And actually, I'm wrong. I forgot. We actually don't want to write this 1 over x plus 5. You want to write the original function. Because what I just wrote, that looks like we could actually plug that 5 in, but we can't. And I got the 1/10 for the x equaling 5 part by plugging in to what we simplified to, this 1 over x plus 5. So now we're going to see how these look visually on a graph. I'm just going to draw a quick graph of the function. So please excuse how rough this is. Okay, we have our vertical asymptote over here at x equals negative 5. Okay, so we have a function that looks kind of like this. So over here at the vertical asymptote, you can see how we can't possibly bend the ends of the function back together. So that's why it's non-removable. And then over here we have a hole, which after we drew in our piecewise function over here, we could actually plug in, which is why it's removable. So that's how you could see it visually by looking for a hole in the graph or a vertical asymptote. And above in the blue is how you could solve for it algebraically. Okay, so now we need to talk about some other things. So the first thing we want to talk about is the properties of continuity. So we're going to have to define some things first. So to look at the properties, we want to let b be a real number, so any number that you know of, and then we're going to let f of x and g of x be continuous functions at the point x equaling c. So when all that is true, 4 different properties come out. So the first is if we multiply some number b by a continuous function at c, we're going to get another continuous function at c. We can also add and subtract continuous functions together to get another continuous function at c. So if we do f of x plus or minus g of x, we're going to get another function that's continuous at c. So along these same lines, we're just going to continue with our other operations. We can also multiply 2 continuous functions at a point to get another continuous function at that point. So multiplying f of x and g of x together is going to be continuous at c. And then if we have division left, so f of x divided by g of x is going to be continuous at c, provided that g of c does not equal 0. So as long as that denominator is not going to be equal to 0 at c, you'll still have a continuous function at the point c. So those are 4 important properties to be aware of. And next we're going to talk about other types of functions. So certain functions are continuous for all x values in their domains. And the first type of these is polynomials. And polynomials, an example of those would be x squared plus 2x minus 15 is equal to f of x. That's a polynomial. Polynomials are continuous everywhere. So you don't have to worry about those. Rational functions would be something like that first example we just saw, that f of x equaling x minus 5 over x squared minus 25. And that's continuous everywhere except where the denominator is equal to 0. So you just have to make sure the denominator of the function isn't equal to 0. That's the only times it's not continuous. And then we have our radical functions, which look like f of x equaling the nth root rather, not just the square root of x. And these are continuous everywhere for two different cases. So it's continuous for all x values, for all x's, if n is odd. So if we have an odd power root, we're continuous for all x values. Positive, negative, 0, everything's fine. But we're only continuous for x greater than or equal to 0 if n is even. So we're only going to be continuous for positive numbers and 0. If we have an even-powered root, you can think of a square root. You can't plug in a negative number to a square root, so the function isn't defined there, so it's not continuous there. And then, of course, we need to look at our 6 different trig functions. So these are important to know, and what's kind of nice is you don't have to remember all 6 of them individually. They pair off. I have the pairings listed for you on the board. So sine of x and cosine of x, they're continuous everywhere. So we're going to abbreviate continuous, but you can plug in any x value and you'll get a y value out. So they're continuous everywhere. Tan of x and secant of x are continuous everywhere except when x is equal to pi over 2 plus or minus n pi. And that just means that like numbers like pi over 2, 3 pi over 2, 5 pi over 2, they're undefined there. And that's because that's where the cosine is equal to 0, and both of these functions have cosine in their denominator if you rewrite them. So you just have to worry about that. And then cotangent and cosecant of x are continuous everywhere except at points that can be written like this. So except when x is equal to plus or minus n pi. So that means like pi, 2 pi, 3 pi, 4 pi, 5 pi, those functions aren't going to be continuous there, and that's because sine of x is equal to 0 at multiples of pi, and cotangent of x and cosecant of x have sine in their denominator, so that's undefined when the denominator is equal to 0, so it can't be continuous. So we have one more property for continuity to talk about, and that's the continuity of the composition of functions. So if we have a function g of x, and it's continuous at an x equaling c value, and then we have another function f of x where that's continuous at x equaling g of c, or the y value when you plug c into the g of x function, then if you compose the two functions, such as f of g of x, written on your board right here, that's going to be continuous at c as well. So that's sometimes helpful to determine the continuity of different functions, which we're going to do in an example right now. So our question here whoops, that is really not proper English. So we're going to have is the square root of 3x plus 7 continuous at x equaling 1. Okay, so we're going to define some things. So first we need to know what our c value is, and it looks like our c is 1 from what the problem says. And then we need to define our f of x and g of x. So we're going to let g of x be what's under the square root, that 3x plus 7. And f of x is going to be the square root itself, so square root of x. Because that way, if we did f of g of x, we would get back what we had in the problem. We would get the square root of 3x plus 7. So the first thing we need to check is g of x continuous at 1? And it is, so g of x continuous at 1. And I can tell you that so quickly because g of x is a polynomial. Polynomials are continuous everywhere, so don't even have to look any further. So g of 1, though, if we plug in, gives us 3 plus 7, or 10. So now we need to see is f of g of 1 continuous. So f of x is continuous at c, or not c, at g of c, or g of 1, or 10. And I can tell you that because that's bigger than 0, which we have the square root function, so our n there is even, 10 is positive, so we can plug in. So Is the square root of 3x plus 7 continuous at x equaling 1? Yes, because we have g of x being continuous and f of x being continuous at g of c. So the whole thing is continuous at c. Okay, so I hope that helped teach you some things about continuity of functions. It's going to be really important for the next video, which is going to talk about one-sided limits. So thank you so much for watching. Have a great rest of your day.